All right, I'll begin with a word of prayer. So, dear Father, we thank you for this day again. I thank you for this class and just ask you to guide our steps today, help us to understand a little bit more about your creation together, Lord. In your name I pray, Lord Jesus. Amen. I need to fix the solution. Like I made a really dumb mistake in problem 1. If you look at the solution to surprise attack mission 3 right now, so I will fix that and repost it, hopefully today. But if you happen to look at it right now and you look at problem 1, just look away. It's hideous. Anyway, okay, so I was in the middle of something last time, you may recall. Let's try to finish that. So we were working on solving mx double dot plus beta x dot plus kx equals to f naught sine gamma t. We wanted to find find choice of gamma, frequency gamma, such that the amplitude of resulting motion is maximized given the system is underdamped. So underdamped in this context means beta squared minus 4mk is less than 0, right? It's the case we have complex solutions to our characteristic equation, and there you go. All right, so we judged from that we could rightly assume that the particular solution had the form like sines and cosines, but I decided to take a different route. I decided to use a complex approach and instead solve mz double dot plus beta z dot plus kz equals to f naught e to the I gamma t, because I told you guys if we could do that, then we could extract from that the real solution. All right, and so we worked this out. We supposed that z was equal to a e to the I gamma t, and found, what did we find? We found that a was equal to f naught times k minus m gamma squared minus I beta gamma divided by k minus m gamma squared quantity squared plus beta squared gamma squared. All right. Now, so to find the real solution here, I need to, look at what's the, I need to look at, my ZP has the form, right? It has the form, that business right there. I should have just written it once up here if I was smarter. Oh well, too late. K minus m gamma squared minus I beta gamma. I think the f naught, man, does that f naught multiply everything? I'm a little suspicious. I bet that f naught, I think I copied it down wrong. I'm pretty sure there's like parentheses here, right? You guys have to look back at last time.
Yes.
Yeah. All right, so f naught. Otherwise it'd be like dimensionally inconsistent. Anyway, so f naught like that. And then my denominator, this contraption, which I probably should just give a name so I don't have to keep writing it, but oh well, I'm going to write it again. M gamma squared plus beta squared gamma squared. All right. Now my e to the I gamma t is cosine gamma t plus I sine gamma t, all right? Now, the theorem I'm using is that the real part and the, both the real and the imaginary part they solve my bad. Well, they solve, in particular, they solve mx double dot plus beta x dot plus kx equal to the real part of f naught e to the I gamma t, all right? And so this would be the x equals to the real part solves this one. Now, what is the real part of f naught e to the gamma t? Well, it's just f naught cosine gamma t, right? We should remember throughout all this that the formula for the imaginary exponential is e to the I gamma t cosine gamma t plus I times sine gamma t. All right? So that's not the thing I'm trying to solve, though, is it? Right? So I'm trying to solve sine. So this is true but not helpful to us. Number two, if we have mx double dot plus beta x dot plus kx equal to the imaginary part of the complex forcing function, which is f naught e to the I gamma t, well, that's f naught sine gamma t, which is actually what I'm after. All right? And here, using x equals to the imaginary part of zp. All right, so finally, getting to the point, the solution that I want is x is equal to the imaginary part of zp. And to figure that out, I would draw your attention to this business up here, all right? If you look at this expression right here, we can figure out what is the imaginary part, all right? So, first of all, there's an f naught up front. I'll just leave that out there. And we're going to have k minus m gamma squared, right? This right here times this guy, because that picks up an I. And there's no sign here, so it's no plus minus sign. There's a sign, though. So sine gamma t. All right? And then minus, looks like a minus beta gamma cosine gamma t, all divided by that big old denominator, k minus m gamma squared plus beta squared gamma squared. All right. Now, let me just rewrite this just a bit. Like, we can rewrite this as x is equal to the force divided by k minus m gamma squared plus beta squared gamma squared times, well, k minus m gamma squared sine gamma t minus beta gamma cosine gamma t. And at this point, I need to rely on some trigonometry that you might not have ever learned, because if I was teaching a trigonometry class, I might or not. I don't know if I would teach this in a given trigonometry class, but it actually matters. Let me share some perhaps unknown trigonometry to you. I'm going to state it as a theorem and resist the urge to derive it today, because I probably should spend my time working other kinds of problems for you guys. But there is a theorem this, if we have C1 cosine theta plus C2 sine theta, then we can rewrite that as something times like the sine of theta plus some phase angle, let's say phi. Do you know what goes in the blank?
C1 plus C2?
Nope. Good idea, though. What if sine and cosine were like perpendicular unit vectors? So you got like C1 in the cosine direction, C2 in the sine direction. Or the square root of C1 squared plus C2 squared in the sine direction. So this is a theorem of trigonometry that, you know, we could try to work out if you like. Like, it's not, if you write this down, it's not too hard to figure it out, like reverse engineer it, right? So like, since it seems like no one has any idea what I'm talking about, this is the square root of C1 squared plus C2 squared, allegedly, right? Adding angles formulas, we've got, you know, like sine theta, cosine phi, plus cosine theta sine phi, right? And instead of calling this square root of C1 squared plus C2 squared, let me just call it M for a moment, or A for amplitude. See, if that's going to be equal to C1 cos theta plus C2 sine theta, right? That suggests what about the, I mean, we have to have A times cosine phi must be equal to what? It must be equal to C2, right? And A times sine phi must be equal to C1 by like independence of sine and cosine, right? And as such, when you put these two together, you got like, you know, A squared cosine squared phi plus sine squared phi factored out the A is equal to C1 squared plus C2 squared. And so there you go. A is equal to the square root of C1 squared plus C2 squared. It has to be that if it's the number which appears there. Of course, I guess there still begs the question, am I sure that I can rewrite a sum of a sine and a cosine as a single sine shifted, right? Well, yeah. This algebra bears that out. So put that into practice over for my formula. You see what I got here? This is C1. This over here is C2. So the amplitude, I've got x is equal to, you know, f naught divided by k minus m gamma squared. I'm writing it again. Squared plus beta squared gamma squared. I'm so tired of writing that. And then the square root of, well, k minus m gamma squared squared plus beta squared gamma squared. I've seen that before somewhere. Times the sine of, well, whatever, you know, gamma t plus some phase angle I don't care about. So lo and behold, this right here, right? I think that simplifies though, right? Because the denominator, and I mean, so we find the amplitude is just equal to, like, you know, f naught divided by the square root of parentheses k minus m gamma squared squared plus beta squared gamma squared. Now, does that answer the question? What was the question that we were asking at the start of all this? You guys remember? It's on the board.
Gamma?
What's that?
The choice of gamma?
Well, yeah, choice of gamma maximizes that amplitude. So how do you figure that out? How do we maximize something in
Derivatives. Optimize
derivatives? Yeah, so we need to, we're trying to vary gamma, right? So we need to look at dA to gamma, right? Differentiate this thing. dA to gamma equals to 0 is what we're going to do. So forget the F naught, that doesn't matter, right? And we have, minus 1/2 k minus m gamma squared squared plus beta squared gamma squared to the minus 3/2 power, right? Times the derivative of the inside, which is going to give me 2m gamma times k minus m gamma squared plus 2 beta squared gamma, I think, if I haven't made a mistake. So I did like chain rule and then the, chain rule again, I suppose. So this right over here, can this be 0? No, that's a sum of squares, so this is not 0. So there's no division by 0 there. And notice over here, we can factor out a gamma. So we can factor out a 2. So I'm going to factor out a 2 gamma times, m times k minus m gamma squared plus beta squared, I think, right? So it looks like either, so solutions, 1, we could have gamma equals to 0. That's the case of a constant force, right? That might maximize the amplitude. That's one possibility, right? Or in the context of the application to circuits, it could be a constant voltage source that gives you the maximum response to an RLC circuit of the same kind of idea. The other possibility, of course, is, gotta solve that. Oh man, this is a what? That equal to 0? I don't know. What's that? M times, I'll write it again here, m times k minus m gamma squared plus beta squared equal to 0. Can we rewrite that? I think we can rewrite. That's minus m squared gamma squared equals to minus beta squared minus mk, which in more civilized terms is gamma squared is equal to, use a me, beta squared plus mk divided by m squared. So the critical frequency would be something like the square root of, beta squared plus mk over m squared, if I haven't made a mistake somewhere. Let me double check. Sadness. I made a mistake. Rats. Where's the mistake? Anybody see it? Go back to here, right? Taking this derivative, right? 2m gamma blah, 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 blah. This 2m gamma was from the derivative of the inside function. There's a minus here. All right? Which puts a minus here. Which puts a minus here. Which makes this a plus, and makes that a plus, which which makes that a mk minus beta squared. Which, of course, we could also rewrite as like the square root of k over m minus beta over m quantity squared, which might be an interesting way to look at it. So what happens when beta equals to 0? What does it reduce to? And does that make sense in a limiting sense? Like what would beta equal to 0 be in this system?
Omega.
Yeah, that'd just be the natural frequency omega squared to k over m for the simple harmonic oscillator, which of course is technically outside of our context because we're in the weakly damped case, right? So like, I'm assuming beta is non-zero here in this derivation, right? Because if beta was 0, then I have to adopt a different particular solution to this problem. I have to multiply by t, like in our previous example, you know? So I can only really take the limit as beta goes to 0 here, but in that sense, it does make sense that we reproduce the natural frequency. And if you like translate this through our dictionary of translation for the RLC circuit, you'll find out that like you reproduce the natural frequency of the LC tank in the limit in the case that the resistance is 0. So it all kind of verifies what your intuition would suggest. But so when you actually calculate this for a system, sometimes this is, sometimes when you plug in the numbers, you get an imaginary number here. What does that mean? Well, that means, what's that? I said, what does it mean if you have a problem like this and you plug in the numbers, you get an imaginary critical frequency. What does that mean here?
Overdamped.
What's that?
Is it overdamped?
No. I mean, suppose you have an underdamped system,
Gotcha.
but you choose values for k and m and beta such that this works out to a negative square root of a negative number. What does that mean? The math has it all here. The math says if this is maximized, it's one of two cases, right? Either gamma 0 or this is 0, right? So if this doesn't work out, then we're back to the 0 frequency solution. Sometimes that happens. I wasn't aware of this, and I assigned this to one of you guys. Like in yesteryear, I assigned this problem, and I was so confused. I was like, "Wait, what?" Because I thought this like always worked, but it doesn't. It can fail. Sometimes the DC, the constant pushing force is the one that gets the maximum response. Anyway, that's that. So I think it's good for you guys to see a hard problem worked out from start to end. And now you've seen one, right? So you guys got any questions? Because we got time for questions.
Is, going back to a cosine phi equals C2, is cosine phi just the directional component of sine theta and vice versa? Is that what it means? Because if A is the magnitude,
Oh.
C1, C2.
Well, here I was just like looking at this equation. So I said, whatever this thing is, call it A.
Okay, yeah.
And then this is adding angles formula for sine. So if I multiply that out, I've got like, A cosine phi is the coefficient of sine.
Oh, I see.
And yeah, I mean, there is a way of deriving these things using phasors, if you know what those are. But I don't, so. And besides, I'm not using a J, so it's offensive, yes? Okay, yes. I could show you what J means to me if you'd like to see.
I'm sure it's very different though, like it is in PE, so.
For me, J is the hyperbolic unit.
Oh.
J squared is 1.
That's still the same.
No. Let me show. Well, may I?
That's -1. It's
May I?
just -1.
May I chase a rabbit momentarily? So you can define something called the hyperbolic numbers as things of the form x plus jy, such that j squared is equal to 1 and x and y are real numbers. In this wild world of hyperbolic numbers, not every number has a multiplicative inverse. If you multiply x plus jy times x minus jy, see what happens. Try it out for yourself. What's x plus jy times x minus jy? So we get like x squared minus j squared y squared, right? Now, j squared is 1. Sorry. C for you, minus 1. And that would make all the difference in the world, wouldn't it? Because if j squared was minus 1, then I wouldn't have x squared minus y squared here. I'd have x squared plus y squared, right? And x squared plus y squared is only 0 when x and y are both 0. But x squared minus y squared is 0 for a lot of other things. So if you take this equation and you think of this thing as z, then basically this gives you the formula 1 over z. Well, it's equal to, apparently, x minus jy divided by x squared minus y squared if, x squared minus y squared is not equal to 0. So this is how like the multiplicative inverse works for hyperbolic numbers, which is already weird because you don't have a multiplicative inverse for like everything on the line y equals plus or minus x. But there's other things. You can talk about the imaginary exponential, as I call it, because I'm an idiot. And how do you think this works out? Now, for you guys, let me use a different looking j. Electrical engineering j theta is cosine theta plus j sine theta, right? How do you think hyperbolic j works out?
Cosine theta minus j sine theta?
Nope. Nope. It's not sines and cosines. It turns out it's cosh and sinh, right? Because if you look at the Maclaurin expansion for this thing, you don't get the plus minus from the squaring of the j. It's just all the positive terms in the exponential series. Half of the even ones go to cosh, the odd ones go to sinh, and there's a j left over. And that's it. You can solve any differential equation with constant coefficients using algebra like this, actually. But I think I'm misbehaving, so I should get back to class. So anyway, I'll make this go away. I spent a few hundred hours thinking about this stuff with students. If you're interested, I can talk to you more. There are open questions. This is a mathematics that's discovered and lost in every generation of mathematicians because it doesn't have a home. Like this stuff was discovered back in the 19th century and then it gets forgotten. It was pretty popular in mathematics, like around the turn of the around 2000, 1900, 1910, somewhere in there. Then it kind of went away. There's a resurgence around 1940, kind of went away. Resurgence kind of around 1990, kind of went away. It just keeps coming back, and people forget it, and then it comes back, and people forget it. But one of my long-term goals is to clarify that kind of calculus and make it make sense. But anyway, so I guess I should work an example for you guys, huh? Let's see here. Let us start out with something pretty simple. We did hard stuff. Let's do something easier. So example 2. What if we were solving y prime prime plus 3y prime plus 2y equal to, I don't know, let's say e to the minus t plus t squared. This is not entirely easy, but it's not that hard either. So can we solve this problem? What do you guys think?
I think you can solve it.
Yeah. I'm not taking your test, though. Well, some days. Although I've often thought about this. Like, we're very concerned about S rates. And I have often suggested that if we just let the professors take the tests for the students, we could increase the S rates dramatically. I mean, we're already doing that online, but not with professors, just with ChatGPT, right? I mean, that's kind of how that works. But So what's the deal? We've got lambda squared plus 3 lambda plus 2. We can factor that, right? So this implies lambda 1 equals to minus 1, lambda 2 equal to minus 2, right? So my homogeneous solution, C1 e to the minus t plus C2 e to the minus 2t, all right? Now I could go through the annihilator method again, but I've went through it a bunch of times and I don't feel like doing it today. So I'm just going to get straight to the point. YP should have the following form. We should do AT squared plus BT plus C. That's the naive, this is the naive guess. However, the naive guess for e to the minus t would be just d e to the minus t, but I don't do that. Why? Because e to the minus t is in the homogeneous solution, right? So I have to multiply that by t in order to make it work. So I do plus d t e to the minus t, because overlap. Can derive via annihilator method, all right? But at some point, we stop driving things and just start using things. So that's this point. Now what do? Differentiate, right? So yp prime is 2at plus b. And got to be careful. That's a product. I need the product rule, right? So d times 1 minus t e to the minus t by the product rule there. And then yp prime prime, that gives me a 2a plus, all right, that's going to give me a d times, well, minus 1 minus parentheses 1 minus t e to the minus t. Now, if you don't like the way I'm differentiating the exponential term, you can do that derivative another way. But we should all agree at the end of the day that the second derivative gives me 2a, plus d times minus 2 plus t times e to the minus t. All right. And then put this all together, right? So we have yp prime prime plus 3yp prime plus 2yp is, well, 2a plus d times minus 2 plus t e to the minus t plus thrice parentheses 2a t, I'll get away here, plus b plus d times 1 minus t. Didn't I say this was going to be an easy problem? What's wrong with me? E to the minus t. That's my yp prime, and then finally plus 2yp. Now, if we did our job right, we should be able to make this all equal to, if you allow me this short manga style calculation, e to the minus t plus t squared. So let us focus our gaze upon the exponential piece. We've got an e to the minus t over here, right? I've got a td e to the minus t, right? But I've also got a minus dt e to the minus t, right? Oh, I can't do math. But there's a 3 here, right? That 3 matters. So I get a plus 1, and then I get a plus 2 over there, so that gives me 2 plus 1 is 3. 3 minus 3, 0. The t e to the minus t terms cancel out. If you do this wrong, that won't happen. And that's math's way of telling you, hey, go to the back to the drawing board, maybe either do the calculus more carefully or reformulate your yp, because you formulated it unwisely, all right? But hopefully we did it right. And so what we have, looking at e to the minus t, is we've got a 1 from the left-hand side. And on the right-hand side, I've got a minus 2d plus 3d. And then over here, plus 2d again, which is, I think, 3d. So my d apparently is just 1/3. All right, d is just 1/3. And then, what else? Yeah, do the. You want to do t squared next? All right, I'll do that one over here. T squared. On the left-hand side, we've got 1. On the right-hand side, we've got what? Oh, just here, right? 2a. So therefore, a is equal to 1/2. All right, got that. Now, how about t? On the left-hand side, do you see the t? It's like an elephant's wings, right? They're set to 0. What's that?
How is it non-existent?
They're set to 0. They exist, they're just 0. Different than non-existent. Elephant's wings exist. They're just set equal to 0. We have to draw a distinction between 0 and non-existence, you know. Okay, I'm just messing with you, but you're fine. 0 is equal to, what we got? Where my t's at? Oh, here's 1, 6a from the middle term. And then 2b. So that tells me that b is equal to what? Notice that 6a is 3 times 2a, which is 3. So I think, what do I get? Negative 3/2. I'll believe that.
I don't know for sure.
I think that's right. That's what I was just seeing.
Professor,
Yep.
is there a reason we don't count the d terms that have a t in them?
Yeah. Because they're also multiplied by the exponential. So they're like a totally different function. But it's a good question. So 1, the constant terms. Again, there's 0 constant terms on the left-hand side, so we have 0 there. So this thing we're doing is called equating coefficients, right? On the right-hand side, I've got my 2a and plus 3b. And man, I'm glad you guys started me with t squared. If I'd started with 1, it would have been much more annoying.
2c.
2c. So we get c equals to what? I'll try to write it out. So I've got minus 1, plus 9/4, is that right? All divided by 2. Minus 1. 3b is minus 9/2, I think. But I have to move it to the other side so I get a plus if I didn't do it wrong. So I think that's a 7/4, yeah. All right, so let's put it all together. My solution then, y is equal to, don't forget the homogeneous piece, c1 e to the minus t plus c2 e to the minus 2t. We can't do anything about that c1 and c2. We're stuck with them unless we're given initial position and velocity or something like that. We need initial data to get that settled past that point. 1/3 t e to the minus t, that's my the last part in the solution. The first shall be last here. And then plus 1/2 t squared minus 3/2 t plus 7/4. All right, there we go. So this right here is like a fairly typical like test question. This is probably worth like 30% of your test if it appears, something like that. I mean, because it's going to take you about 30% of the time on the test to do this problem. But it is a problem you should be able to do.
Professor, how necessary is it that we be able to do this without the annihilator method?
I'd say it's important to be able to do both. So I'd say it's pretty important. Yeah. So the point of the annihilator method is actually to do enough of those so that you gain an intuition about how you build these solutions. The alternative to this is to look at Nagel, Saff, and Snyder and read the theorem about how to construct solutions. That theorem is about this long, right? And it's got like 6 different cases and a bunch of like hard to follow indices and junk in it, right? But it boils down to look at the homogeneous solution. If there's overlap, pick on those pieces and fix them. Now, there are things that can happen. Let me show you something that could catch you off guard. Suppose we're up against y prime prime plus y prime equals to, oh, I don't know, 2 times the hyperbolic cosine of x. Solve this problem. So while I'm moving the camera, you guys find the homogeneous solution. Tell me what it is. By the way, isn't this easier than the start of the course? Like, I don't know. To me, this is much easier than like the integration part. You know, like you just don't know what's lurking around the corner in terms of like Calc 2 you've forgotten. But anyway, so okay, so we've got lambda squared plus lambda, which is lambda times lambda plus 1 equals to 0. So I either get lambda 1, which is 0, or I get a lambda 2, which is minus 1. All right? So my y homogeneous would be like c1 plus c2 e to the minus x. Right? And at first glance, it might look like that's okay. But what's the problem with Koch? Well, yeah, but what does it mean? Right, I mean, you guys know that it's the e to the x we can rewrite as, 1/2 e to the x plus e to the minus x, right? 1/2 e to the x minus e to the minus x. In other words, this is Koch. This is sinh. Koch and sinh are respectively the even and the odd part of the exponential function. But anyway, the definition of Koch is 1/2 e to the x plus e to the minus x, you see? So, truth be told, what you're up against here is e to the x plus e to the minus x, right? And once you write it like that, then all of a sudden you can see that this right here is a problem. Right, I have to adjust the particular solution to reflect that reality. So the particular solution here, I would write down like this: a e to the x plus bx e to the minus x, because that part overlaps. And that should work for me here. Like, let's work it out. Yp prime, a e to the x plus b times 1 minus x e to the x, 1 minus x times e to the minus x. Yp prime prime, a to the x plus b times minus 1 minus x e to the minus x, which I can clean up a bit. So put these guys in to yp prime prime plus yp prime equal to e to the x plus e to the minus x. And what happens? Well, you got a e to the minus x. Oh, wait a minute. I did a bad thing. right here, right? Sorry about that. Because it was there's no minus on the a term. Did it here too. So a to the x plus b times minus 2 plus x e to the minus x. That's my yp prime prime term. And then yp prime is plus, we write it in a different color. A e to the x plus b times 1 minus x e to the minus x, right? And that's all equal to e to the x plus e to the minus x, right? Come on, board. Anyway, now if we did this right, the x e to the x terms, they've got to cancel. See how that happens? I got this one here, and this one here. I got a plus bx, I've got a minus bx. They're gone. They nuke each other. That's important. This mutually assured destruction gives us hope for the solution here. So 2a e to the x. It does sound kind of wrong, I guess. But anyway, all right, so what we got? We got b times minus 2 plus 1 e to the minus x is equal to e to the x plus e to the minus x, I think. The x terms be canceling, and so we see from this 2a is equal to 1 and minus b is equal to 1. So a is a half, b is minus 1. My solution is c1 plus c2 e to the minus x plus 1/2 e to the x minus x e to the minus x. I should mention, for the hyperbolic exponential, like if the problem wasn't like this, right? If instead I had something like y prime prime plus y equals to 2 cosh x instead, that would be a different problem, right? And that would be a much easier problem. Yes, go ahead.
For once you simplify for plus b, it's negative 2 plus 1. Oh, I see what. Sorry, I'm being slow. I apologize.
No, it's fine. Fine.
No, you did your math right. I was like, why
It's all good.
did it's supposed to be b times 1, right?
Trust.
So it ends up, and you did it right.
Trust. No. Trust but verify. I make mistakes for real. I definitely make mistakes. I can prove it to you. So here, hopefully not now, but this right here, there's no overlap. The reason being the homogeneous solutions for this one, this is lambda equals to plus or minus I, right? So my homogeneous solution is like c1 cos x plus c2 sin x, and those are totally different animals from cosh. So in this case, I can just write the naive solution, which I wanted to share with you. It's simply this, a cosh x plus b sinh x. And check this out. Yp prime prime is equal to yp. Because the derivative of cosh is sinh, and the derivative of sinh is cosh. So when you double differentiate this thing, you just get back to where you started. And as such, yp prime prime plus yp is just equal to 3, not even 3, 2 yp, which is equal to 2 cosh x. Therefore, yp is cosh x. And solution is simply c1 cosine x plus c2 sin x plus cosh x. So these problems can be easier, like this one. The overlap slows me down a lot because it makes us do product rule and stuff. What happens if you don't put the x where it belongs and you try to work out the solution? What happens? You will get a contradiction. You'll get 0 equals 1, stuff like that. Don't ignore that. Let the math speak to you to go back to the start and to fix what you did. You know? Anyway, I'll shut up. I think that's it for today. Oh, I'm sorry, I went over. It was for a good cause. Did I hand the... Oh, man. Just peace be with you. We did we top hatted it. It's enough. I will eventually hand that sheet around. I'm sorry, guys.